The purpose of maintaining abstraction barriers is so that you can change your data representation without having to rewrite your entire program. Let's poke a little bit deeper into this idea of data representation. What is data? What does it mean for something to represent a rational number? Well, we need to guarantee that the constructor and selector functions work together to specify the right behavior. You don't have a representation of a rational number unless it behaves like a rational number. A behavior condition would read something like, if we construct rational number x from numerator n and denominator d, then it should be the case that numer x divided by denom x equals n divided by d. Here we relate the constructor, called on n and d, to the selectors and an operation between them. Data abstraction uses selectors and constructors to define behavior. That's the whole idea of data abstraction. If the behavior conditions are met, then the representation is valid. So the key underlying idea related to data abstraction is that you can recognize what sort of data something is by its behavior, not necessarily by how you constructed it or how you implemented the constructor and selectors. So let's look back at our example. We have add, mul, an equality measurement, and a way of printing rational numbers. All of this doesn't assume anything about the representation itself, only that the constructor and selectors exist. The constructor and selectors, below this abstraction barrier, are implementing rational numbers in terms of lists. So it's the case that I can say x and y are the rational number 1, 2, and the rational number 3/8. I should say 1/2 and 3/8. So what happens when I print the result of multiplying together x and y? I get 3/16. It should be the case that I can change my representation, and all of this will still work. So here we go. Instead of using a list to couple together n and d into one thing, we're going to use a function. We're going to define a function called select, which takes in some name. If that name is n, then it's going to return the numerator. Otherwise, if the name is d, it will return the denominator. And what else? Well, we're not going to worry about those other cases. We'll just return the select function from the rational function. Now, it must be the case that the constructor and the selectors are complements of each other. That when you construct something with the rational constructor, you can then select its numerator using the numer function. So if x is the result of calling rational, then it's a select function, which I can call on n to get the numerator. And likewise, I call x on d to get the denominator. Let's try our example again. I set x and y to be 1/2 and 3/8. I then printed the result of multiplying x and y together, and I got 3/16. Did we really change anything? Well, certainly we did, because x is now a function. So that's a change in representation that led to another valid representation of rational numbers that works just as well with our old code as what we had before, but uses an entirely different mechanism to keep track of the numerator and the denominator. And notice that we did this with just functions. We didn't actually need that built-in list data type at all. So what exactly happened when we implemented rational numbers as functions? Well, we defined the constructor and selectors, and it was this function, the select function, that represented the rational number. It was returned by the constructor, which was a higher order function. And the selector just called the function that resulted from calling rational in order to get the numerator back. by defining a function within another function, we were able to refer to the n and the d in the enclosing scope. And so this select function that we returned did have carrying with it the numerator and denominator that we wanted to access later as part of its parent frame. So let's say, a simpler example, we set x equal to rational 3/8, and then we ask for the numerator of x, which should be 3. The environment diagram looks like this. Rational numerator and denom are defined, and then we call rational on 3 and 8, which creates a select function whose parent is the f1 frame where n and d are bound. That's returned and bound to x equals rational 3/8. Once we have x, we can ask for its numerator, which creates a new frame in which x is bound to the select function. The body of numer says that we're supposed to call x on n, so that's exactly what happens in this third frame, f3, where name is bound to n, the body of select is executed, name is n, and so it returns n. Looking here, we see that the name n is not defined, but if we look in the parent f1, n is bound to 3, and so that's what's returned.